Okay, so let's start as usual with the review from last time. So last time we introduced Minkowski's hyperboloid by means of Minkowski's form, right? Actually, by means of the quadratic form associated to Minkowski's form, and we defined the Lorentz and proper Lorentz groups. Well, the Lorentz group as the group of bijective linear as the group of matrices of 3 by 3 matrices with the real entries that preserve the Minkowski's form, and the proper Lorentz group was just those that have determinant 1. Right? And that's pretty much what we did. This we are going to do in today's lecture, but no in the review. Yeah, I think so. Yeah. So this is actually part of today's lecture, not the review. Okay. So we introduced Minkowski's form as the function from R3 Cartesian product R3 to R given by this formula, right? And kind of the Minkowski's pairing of two vectors in R3 is almost the usual inner product, almost the usual interior product, except that when we pair the third coordinates, we do it with a minus sign. Right? So, but somehow it really just kind of a minor change, and somehow this minor change kind of produces everything that comes after. Right? Obvious, well, this gives an R bilinear symmetric and non-degenerate function, right? A symmetric non-degenerate bilinear form, and also it's easy to see that it's not an interior product. Well, simply because, for instance, the vector 0, 0, 1 paired with itself gives me minus 1. So it cannot be an interior product, right, or an inner product. Okay, but nevertheless, we consider the quadratic form associated to that bilinear form, and we consider like the level sets, right, and the hyperboloid model for the hyperbolic plane will arise as the level set will arise from the level set at a specific value, right? Kind of when considering the points that that make this satisfy an equation, right? Which actually is going to be this constant to -1. Okay, then we made some basic considerations, like some analytic geometry considerations, kind of so as to justify that for when the constant is negative, its level set looks like a two-sheeted hyperboloid, right? A hyperboloid of 2 sheets. Right, so somehow these curves that you are seeing here are actually supposed to be hyperbolas, right? Not parabolas. Okay. Yeah, and then somehow one of the points we made is that when we let c go to -infinity, somehow the sheets of the hyperboloid get far away from 0. And then when we let -c, come close to 0, somehow the two get close to each other, right? And when c is 0, somehow these two sheets coming together, kind of the picture gets kind of degenerate, and it produces this two-sided cone, right, known as the light cone. And then from here I now get positive values of C and I let them get away from 0, like to the right, then what I get is a one-sheeted hyperboloid that, as C goes to infinity, starts getting like thicker and thicker. Right? So those were the three situations, and we defined. We considered, as I said, the level set for -1. So this is the x, y, z's that satisfy this equation. So this really is a hyperboloid of 2 sheets. So we considered only one of them, right? The one that lies kind of on top. And we said that such a sheet of that 2-sheeted hyperboloid, we are going to simply call it the hyperboloid. And then here you can see an expression of the hyperboloid as the graph of a function from R2 to R, right? Kind of the graph of the function from R2 to R, given by f of xy equal to x squared plus y squared plus 1, plus 1 square root. Which is nice because, I mean, kind of this is the advantage that this gives me, the advantage of being able to see M as the graph of a function from R2 to R, is that at any point of the hyperboloid, I can compute the tangent plane, kind of the subspace of R3 tangent to M at P, using just calculus 3, right? Kind of just analyzing precisely that function f that I said, right? This function f from R2 to R, given by f of xy x squared plus y squared plus 1 square root, because if you see, kind of, if in a calculus of 2 variables, they ask me, okay, compute the tangent plane at the graph of this function at any point, you see, then my point on the plane would be just xy. The point in the hyperboloid would be this one, so it would be the point on the graph, and kind of, if you revise kind of your calculus textbook, what one ends up actually doing is computing these vectors, right? So this is actually the partial derivative of this with respect to x, and this one is the partial derivative of this one with respect to y. Okay, and then the proposition is that tangent plane is actually can be computed as the Minkowski orthogonal to the point in M. Right. So somehow the proposition tells me, okay, so you can do this using calculus, but you see, but there is a faster way. It's kind of just compute all the vectors Minkowski orthogonal to your point, right? And well, for the proof overall uses that one knows that both of them are two-dimensional. The fact that this is two-dimensional follows from the non-degeneracy of Minkowski's form, and then one uses that one knows that this is a basis, because then one just pairs this with P and this with P, and one finds that those pairings are 0. So one obtains this inclusion, but then since both of them are two-dimensional, one has equality. Okay, and then recurring to Cauchy-Schwarz inequality for the inner product on R2, so the kind of the well-known inner product on R2, one can show that for each P, when one takes Minkowski's product but kind of only looks at the Minkowski's product on the tangent plane to M at P. On this two-dimensional space, it is an inner product. So it's not an inner product. So somehow the picture, the kind of the rough picture is that Minkowski's product, Minkowski's form is not an inner product for R3, but for these special vector subspaces, which are the tangent planes to the hyperboloid. On those, which are always just two-dimensional, on those it does define an inner product on each of them. Right? So, okay, and then kind of one just proves it. Yeah, and then knowing that for each point it gives me an inner product on the tangent plane. One can compute for each P the matrix of this as a bilinear form, right? And then when one computes it here, right? You have to use a basis. Which basis do you use? Well, precisely this one. Yeah. Okay. And then when we compute it with respect to that one, we see that the matrix is given in these terms, right? Where here my point P is given by the entries A, B, C. And one sees that the entries of the associated matrix are defined smooth functions of A, comma B. Right? And so somehow this means that the matrix varies smoothly as I move P in the hyperboloid. Right? So somehow what I'm verifying is that Minkowski's hyperboloid becomes a two-dimensional Riemannian manifold under Minkowski's form. More correctly, by considering Minkowski's form restricted to each of the tangent planes at the points of the hyperboloid. Okay, and then we gave a definition that will keep playing a role, which is the notion of Riemannian isometry. So, two Riemann manifolds are a Riemann isometry between two Riemannian manifolds is a diffeomorphism between them, right? A diffeomorphism between them, with the property that when we have a point in the domain and two tangent vectors at that point, measuring the inner product at them is equal to measuring the inner product at their images on the derivative of the function at the image of the original point under the function. Right? So here is the picture, right? And it's kind of it's really a simple concept. It's just that the notation becomes the formula becomes maybe a bit intimidating at first glance, but the idea is simple to describe, right? I mean, if I have my diffeomorphism, I have, which I'm sketching here, for each point in M, I have its image, right? And then I can compute the tangent plane or space more generally at the domain or at the codomain, right? So yeah, and then in the tangent plane that at the domain, I can take any two vectors and then pair them, right, with the inner product, with the interior product that makes M a Riemannian manifold, or I can pair their images under what can it be? Under the derivative. Right? So under the derivative, I can move to N, and here I can take their inner product using now the Riemannian structure on N, and I call F a Riemannian isometry if the inner product here in the domain is always equal to the inner product on the images in the codomain, right? So which is this formula, and this is always, right? This is everywhere, so it's for every P and every pair of vectors, of tangent vectors to M at P. Okay, and the point is that we are interested in studying the Riemannian isometries of the hyperboloid because now we have a Riemannian structure on the hyperboloid. I mean, we have for each point of the hyperboloid an inner product on the corresponding tangent plane, and this inner product moves smoothly as we move the point in the hyperboloid. And so we want to study this kind of the self-isometries of this, the Riemannian isometries of this space. And then kind of we just made some considerations as to why it is a good idea to try to see our groups as groups of matrices, right? And then somehow we are the point is that we are going to try to see the isometries of the hyperboloid, the Riemannian isometries of the hyperboloid, not only by considering kind of the hyperboloid itself, but but we're going to see them as coming as restrictions from linear maps from R3 to R3. Just like here, we saw the translations of the Euclidean plane as coming from 2 by 2 complex matrices, right? By seeing our Euclidean plane as sitting inside C2 at height 1, right? So it's kind of similar. We really consider the hyperboloid sitting as the hyperboloid in R3. And this brings us to defining our first two groups, which are the Lorentz groups. The Lorentz group, which is simply the group of 3 by 3 invertible real matrices that preserve Minkowski's form pretty much, and inside it we take those matrices in the Lorentz group that have determinant 1. Right, and then a characterization, right? A characterization that pretty much relates preserving Minkowski's form, you know, for arbitrary pairs of vectors, and simply kind of preserving this matrix, this 1, 1, minus 1, and preserving some of the most important level sets of the quadratic form associated to Minkowski's form, and so one corollary is that for every element in the Lorentz group, we have that A multiplication by A, as kind of this is just multiplication of matrices. I mean, right? I mean, kind of this is the image of M under multiplication of its points seen as vectors with the matrix A, and the corollary is that each element of the Lorentz group either preserves the hyperboloid bijectively, or it sends it to the sheet downwards, to the sheet kind of downstairs, underneath, right? So somehow this is really not the group, not quite the group we are looking for, because its elements, not all of them preserve. That's the point, and